Welcome to Unit 3. This unit is all about ions and ionic compounds. And so let's get started. The first thing that we want to see is that bonding is the joining of two atoms in a stable arrangement. Let me change my pen. There we go. In bonding, electrons will either gain, they will lose, or they will share electrons to reach the electron configuration of what's called noble gas configuration. That's the noble gas that's the closest to them on the periodic table. If you remember what we learned about noble gases, they have a full octet and therefore are stable atoms, and so all atoms would like to have that same stability, and so in order to achieve this, they have to form bonds with other atoms, and so their goal is to have a full octet of electrons. We're going to look at two different types of bonding. The first one we are going to focus on in this unit is ionic bonds. They result from the transfer of electrons from one element to another. And then when we get to Unit 4, we're going to focus on covalent bonds. Covalent bonds result from the sharing of electrons between two atoms. So ionic bonds are a transfer of electrons, and covalent bonds are sharing the electrons within that bond. All right, so let's take a closer look at ionic bonds. Ionic bonds form between a metal, which you find those on the left side of the periodic table, and a nonmetal. The nonmetals are on the right side of the periodic table. So when you have an ionic compound, it consists of a metal and a nonmetal. So here in the pictures we see that we have sodium metal. So sodium is element number 11 on the periodic table. And we also have chlorine gas, which we find all the way over to the right-hand side in group 17, the halogens. Chlorine gas is element number 17. When we combine these two through a chemical reaction, we get something called sodium chloride. And sodium chloride is simply table salt, the same salt that you would have in your kitchen. And so you can see that evidence of a chemical change where we have a brand new substance. When we look at the reactants, the sodium metal is a silver shiny piece of metal. Chlorine gas is a deadly green colored gas. But when the two of them combine chemically, they form something that we use every day to season our food, sodium chloride. Covalent bonds are formed when two nonmetals combine. And so two nonmetals, or possibly a metalloid and a nonmetal, can combine to form what's called covalent bonds. Another term that you need to know is molecule. A molecule is composed of elements. Let me back up. A molecule is a compound or an element containing two or more atoms joined together with covalent bonds. So most of the time, when you hear this word molecule, you would think of a covalent compound. And again, these covalent bonds will be discussed more when we get to Unit 4. The focus in this unit is going to be about ionic compounds. And so let's take a closer look at what an ion is. And so ions are charged species in which the number of protons and electrons in an atom is unequal. So when the number of protons and electrons are the same, you just have a neutral atom. But when anytime that you have more or less electrons, then that creates something called an ion. And so ionic compounds consist of oppositely charged ions that have a strong electrostatic attraction to each other. So this word, electrostatic attraction, is something that we'll see a lot in chemistry, and it simply means this attraction between opposite charges. So when you have a positive charge and a negative charge close to each other, there is an attraction between them. Like charges repel, opposite charges attract, just like in a magnet. So there are two types of ions. One is called cations, and the other are anions. Cations and anions are the two types of ions that we'll be looking at. So cations are positively charged ions, and a cation has fewer electrons than protons. So when a cation is formed, it is the result of losing an electron. One way to remember that cations are positive is by writing the word with this big T in the middle. And so this T just helps you remember that cations are positive. And so you can see in the picture here we have sodium. Sodium has 11 protons. This particular sodium isotope has 12 neutrons, and the neutral atom has 11 electrons. So 11 protons and 11 electrons, which makes it a neutral atom. Let's review the electron configuration for sodium. We have 1s2, 2s2, 2p6, 3s1. So remember that at the very end are our valence electrons, and so sodium being in group 1 has 1 valence electron, and we can see that here in the electron configuration. So if sodium were to lose that 1 electron, then we would have 11 protons still, but now we only have 10 electrons. And so when you take the 11 protons, remember protons are positive, and now we have 10 electrons, and electrons are negative. If we were to add these numbers together, we would get +1. And so this ion of sodium is going to have a charge of +1. And so that is indicated by this symbol here. You have the sodium's chemical symbol, and then you have a plus sign in the upper right-hand corner to show that that atom has lost an electron. If you'll keep in mind that electrons are negative, and so when you lose a negative electron, the charge is going to become more positive. You might think about this in terms of your attitude. If you have a negative attitude, if you lose that negative attitude, you're going to become more positive. So that may be a way to help you remember. The next slide says, by losing 1, 2, or 3 electrons, an atom forms a cation with a completely filled outer shell. So the whole reason behind forming ions is so it can achieve this full outer shell. And so when we look again at sodium's electron configuration, this one's magnesium, we see that the magnesium ion has 2 valence electrons that we see here, 3s2. If magnesium were to lose those 2 electrons, then we can see, based on this electron configuration, that it now has 8 valence electrons in the second sublevel. So it has achieved this full outer shell. Now its second sublevel is its outer shell, and it has 8 valence electrons. Let's look at anions. Anions are negatively charged ions, and an anion has more electrons than protons. And so an example of that is our chlorine atom. You see that chlorine has 17 protons and 17 electrons, so that makes a neutral atom. If that, notice the electron configuration down here. You see the valence electron configuration is in red, 3s2, 3p5, that's that 7 valence electrons. But what if chlorine were able to gain 1 electron? So now you have 17 protons and 18 electrons, and notice it now has a full outer shell. So that was the whole purpose of forming an ion. Chlorine gained 1 extra electron so that it could fill its outer shell. We can relate the group number on the periodic table to ionic charges, and so there is a way of looking at the periodic table to see what type of charge the atoms in that group would form. And so metals always form cations. Metals form cations. And so if we look at metals in group 1, group 2, and group 13, then the group number is equal to the charge of that cation. So in group 1, all of the elements in group 1 will have a +1 charge. All of the elements in group 2 have 2 valence electrons, and therefore will lose those 2 and have a +2 charge. And all of the elements in group 13 will have a +3 charge. Let's look at the anions. So nonmetals form anions. And for nonmetals in group 15, group 16, and group 17, the anion charge is equal to 8 minus the group number. A simpler way that you can look at that is just look at the ones place of the group number. So if we're in group 15, we're just going to look at the ones place, which is 5. So all of the atoms in group 15 would have 5 valence electrons. All of the elements in group 16 would have 6 valence electrons, and all of the elements in group 17 would have 7 valence electrons. So you can memorize this little formula, if you will, or you can just remember to take the ones place of the group number. The ones place of the group number, and that will work as well. All right, we have a chart here for the main group elements. Remember, we have main group elements and then we have transition elements. And the transition elements typically don't follow the same rules that we're learning. So there is a distinction between these main group elements and transition. And so here you see the group number. Remember, there's 2 different ways that the periodic table can be numbered. I believe the one that I gave you to run off has numbers 1 through 18, and so that's what you see here in parentheses. You can refer to those. And so let's go through this. In group 1, there is 1 valence electron, and therefore 1 electron is lost. Since these atoms only have 1 valence electron, if they were to lose that 1 electron, then they will have a full outer shell. And so the ion symbol that's written is just simply the chemical symbol with a plus sign in the upper right hand corner. There's no need to put 1. It's understood to be 1 when you don't see a number. So just the chemical symbol, for example, sodium with +1. Now when you get to group 2, they all have 2 valence electrons, and so these atoms will lose 2 electrons. 2 electrons are lost, and the symbol is the chemical symbol and then a 2+. For example, magnesium is in this group, and so you would have Mg and then a superscript of 2+. Group 3, we can have 3 electrons lost to fill that outer shell, and the symbol is M3+. So aluminum is one of those elements. So Al with 3+ in the upper right hand corner. And then we run into some nonmetals, and so these are anions that are going to be formed. So this time in group 15 we have 3 electrons that are going to be gained. So instead of losing electrons, now we're gaining electrons. And so we see the symbol is changed. Again, we're going to have the chemical symbol and then a 3-. So nitrogen is an example of that. So the chemical symbol N with 3-. In group 16, we have 6 valence electrons, and so we just need to gain 2 more in order to get to 8. So 2 electrons are gained. And the symbol would be the chemical symbol and then 2-. So oxygen would be an example of this. And then we have group 17. And in group 17 we have 7 valence electrons, so 1 electron needs to be gained to get to that number 8. And we write the chemical symbol and a negative sign. And again, you don't have to put the 1, it's an understood 1. So just the symbol and the name. Alright, here are some other charges that are commonly used, and so you can see from their location on the periodic table that they have the same charges. It's helpful if you will take out your periodic table that you've been writing on, and if you would just go ahead and write the charges at the top of that table, that would be very helpful. Let's see, let me just write on this one for you to show you. So I would just take my pen and I would put a +1 here, +2, we'll go over here to +3, then we have -3, -2, -1. Now this group 4, or 14, excuse me, this can form either +4 ions or -4 ions. So think of that as kind of the tipping point between your cation and your anion. Alright, let's talk about this transition metals. Remember, these are the transition metals here in the middle. And again, these metals typically don't follow the rules that we learn, and so their charge is the same. They have, some of these elements have multiple charges, and so these are listed here for you, and you might even just want to make note of that on your periodic table. Some of these that we use quite often, zinc is one, and notice zinc only has a +2 charge. Silver is another one that was used quite a lot, and it has a +1 charge. We tend to use iron a lot, and it can be either +2 or +3. We also use copper quite a bit, and so it can be +1 or +2. So you might want to add these to your periodic table. Here's another one that we use an awful lot, lead. Lead can be +2 or +4. And so those are some of the transition metals and other metals that have multiple charges. And so I will show you as we get to writing formulas how to use these charges to write correct ionic compounds. If we look at some ions that we find in our human body, they're quite important to us. In our teeth and bones, we have calcium ions. You can see that sodium and potassium are found in many of our body fluids. They also help with muscle contractions and things like that. Iron 2 in particular, is found in our blood, in the hemoglobin of our blood, and that's what carries oxygen in our blood, so that's very important. Chloride ions are present in our gastric juices and stomach fluids and other things. And then it shows magnesium 2+ is needed for nerve transmission and muscle contractions. So you can see all of these chemicals are very important in our body. All right, let's talk a bit about ionic compounds. And so an ionic bond is formed when a metal transfers one or more electrons to a nonmetal. And so we said previously that metals tend to form cations, and remember cations will lose electrons, and so that electron that the metal lost is transferred to the nonmetal, which like to gain electrons. And so the sum of the charges in an ionic compound must be 0 overall. So when we're forming a compound, we have to make sure the charges add up to 0. So here is the example given to you. You have sodium ion and you have a chloride ion. Notice the charges. We have +1 and -1. When we put those together to make our new compound, sodium chloride, the charges add up to 0. So anytime you have an ionic compound formula, the overall charge of that compound is always going to be 0. Here's a couple more examples. Here we have calcium 2+ ion. It has a 2+ charge, and the fluoride ion has a -1 charge. And so when we look at these charges, when we add the charges together, they do not equal 0. So +2 -1, that would be a +1 charge. And so we need to add another fluoride ion so that we could add all of these charges together, and the overall charge would be 0. So we have calcium 2+, fluoride, each with a -1 charge. So 2 fluoride ions were needed to make the overall charge add up to 0. Here are a couple of other examples. We talked about this one, sodium chloride. Here we have lithium ion and an oxide ion. Each of the lithium ions is +1, and so notice that there's 2 of them to balance out this -2 charge so that they could add up to be 0. And notice how the formula is written. We'll learn more about this a little bit later, but there's a small 2 showing the number of lithium atoms. When you have a subscript, it follows the atom that it is talking about, follows the element. The next example is barium with 2+ paired up with iodide. And so iodide, each of the iodides have a -1 charge, and so we needed 2 of those to balance out the charge. So here you see the formula BaI2. Remember, the subscript describes the element that it follows. This one's a little bit more complicated. We have aluminum 3+, and we have oxide, each with a -2 charge. And so when we look at the +3 and the -2, one way to look at this is to think about what is the least common multiple that they have in common. And the least common multiple is 6. And so you have to think about 1 aluminum with its +3 charge. What do we need to multiply the 3 by to get to 6? Well, that answer is 2. So we need 2 aluminums. And then for oxygen, that least common multiple is 6. What do I multiply 2 by to get to 6? We multiply 2 by 3 to get to 6. And so we have Al2O3 will be the formula for aluminum oxide. All right, let's go into a little bit more detail about how to write ionic formulas. So the first thing it says to do is to identify which atom is the cation and which atom is the anion. So just a reminder, metals always form cations and nonmetals always form anions. And so once we've identified the cation, then we want to use the group number to determine the charge. And so let's practice that. Grab your periodic table, and if you find calcium, we'll see that calcium is in group 2A, or group 2. Calcium is in group 2. It is a metal. And we see that in group 2, all of those atoms form a 2 plus charge. Calcium 2 plus. Next, we want to look at oxygen. We see that oxygen is a nonmetal. So it's going to be on the right-hand side of your table. Oxygen is in group 16. It has 6 valence electrons. So you have to think, how many electrons am I going to need to gain in order to get to 8? And so for oxygen, it needs to gain 2 more. So it takes on a -2 charge. Our last example is chlorine. And chlorine is a nonmetal found in group 17. Remember, the group number tells us how many valence electrons go in with that ones place. We see that chlorine has 7 valence electrons. And if it could gain 1 more electron, it would have a full outer shell, and so it's going to take on a -1 charge. All right, moving on to step 2. Step 2, you want to determine how many of each ion type is needed so that the overall charge is 0. So when the cation and the anion have the same charge, then only 1 of each is needed. And so here we see an example of that. We have the calcium 2 plus ion and the oxide 2 minus ion. So they have the same charge, therefore only 1 of each is needed. And so the formula that we need is CaO, 1 of each. And when we add those up, the charge is equal to 0, which is our goal. Always want the charges to be equal to 0. When the cation and the anion have different charges, then we use the ion charges to determine the number of ions of each needed to have an overall charge of 0. So let's practice with this one. Calcium ion, 2 plus ion, and chloride with a -1 charge. And so here we have 2 plus and -1. We add those together, we see that it does not equal 0. And so we want to think about what is the least common multiple. What's the smallest number that both of these have in common? When we think of our multiples of a 2, we see 2, 4, 6, 8, so on. When we think of our multiples of 1, it's 1, 2, 3, 4. And so the least common multiple between the two is the number 2. So we want to make both of these equal to 2. So when we look at calcium, we see it's already 2 plus, so that means we just need 1 calcium. But when we look at chloride, it's a -1. So what do we multiply by -1 to get to 2? We would multiply it by 2. And so that's telling us that we need 2 of the chloride ions. And so when we have 2 chloride ions, that equals a -2. We add those charges together, that's -2. And then we add that to the +2, and we get an overall charge of 0, which is our goal. All right, to write the formula, you're going to place the cation first. Every time in an ionic formula, the cation goes first, followed by the anion. And you want to omit the charges. You will never have charges in an ionic formula. So we use subscripts to show the number of each ion needed to have this overall charge. When there's no subscript written, it's assumed to be 1. So again, you don't have to write the 1. So 2 examples here, calcium oxide and calcium chloride. All right, let's move on to naming ionic compounds. And so we can look at how to name individual ions. And so you have your main group ions. This is group 1, group 2, and group 13. To name these main group ions, their name just comes from the element from which it is formed. So Na+1 is simply named sodium ion. K+1 is potassium ion. Ca+2 is a calcium ion. And then Mg2+ is a magnesium ion. So cations are easy to name. They're just named after their parent element. When an element is able to form 2 different cations, as we saw with the transition metals, their name is a little bit different. So there's 2 common ways to name these. There's the systematic naming system, which uses Roman numerals. And so it says you follow the name of the cation by a Roman numeral in parentheses that indicates the charge. So this is probably the most common method of naming. Sometimes this is referred to as the stock system of naming. And you may have seen some compounds written with Roman numerals in the past. So we'll see some examples of these along the way. There's another way of naming these called common names, and they use the suffix OUS for the cation with the smaller charge, and the suffix IC or IC for the cation with the higher charge. And so we see an example here. We have Fe2+ and Fe3+. So instead of using Roman numerals, another way that this can be written is by using the Latin word for Fe, which is FERR, and then the smaller charge gets the OUS ending, so you have ferrous, and the higher charge gets the IC ending, and so you have ferric. And so the next slide has a table of these common names as well as the systematic names. And so you see how each of these are used. Notice the common name of copper is cuprous, and this is where the symbol Cu comes from, cuprous and cupric. As mentioned earlier, ferrous and ferric, and this is where the Fe symbol comes. This is from the Latin word that means iron. Mercurous and mercuric. Tin, this is where the SN name comes from. The Latin word for tin is stannous, and stannic. And so that gives you an idea of where some of these symbols come from. Now when we're naming anions are named by replacing the ending of the element name by the suffix IDE. So anytime you have an anion, you simply change the ending. Bromine becomes bromide. Bromine becomes chloride. Fluorine becomes fluoride, and so on. And so for the metal cations, they just take on the name of their metal. But for anions, you actually have to change the ending. Okay, I'm going to stop this video here and take up with part 2 for our rest of our slides.